Welcome everybody to Cultivate by Forbidden Root in the north side of Chicago. We're a brew pub with a lovely restaurant up here in the Lincoln Square neighborhood. My name's Randy Mosher. I've been kicking around in the homebrew and brewing worlds for quite a few years. Today, we're going to be talking about tasting. So the talk is entitled, "This is Your Brain on Beer." So this is really trying to get an understanding of all of the neurological and psychological processes that are involved in tasting. It's quite complicated in its essence, but in reality, these are all things that we experience directly. So what I'm going to tell you is really just the kind of the nuts and bolts explanation for it. And then as we get towards the end, we'll dive in a little more deeply into the actual practice of tasting and pouring, how to pull a beer apart into its component parts. So that's going to be the presentation today. Everybody knows how to drink, I presume, but not everybody knows how to taste. And it's important to really understand that these two things are not the same. Drinking, of course, you're getting with your friends, you're just trying to have fun and have a beer, relax, not think about it too much, which is absolutely lovely. I love to do that myself. But tasting is really always done with a particular purpose in mind. When you're tasting, you're really trying as much as you can to ignore the sort of just subjective aspects of it and really kind of focus on what is coming into your senses, into your mind. And it takes a little practice to do it. The more you practice at it, the better you get at it. And over time, you develop a vocabulary and you develop the tasting skills to really become better over time. People do it for purposes of quality control. They do it like we're going to do it here for educational purposes. We do it quite often at our breweries to try and help people understand what our beers are all about and walk them through it, trying to tell them the stories behind the beers. You want to taste the competition, hopefully, to understand what they're doing. So we have a few things we can work with. Those are our senses. We rely very heavily on vision, but that is not that much involved in tasting, honestly. So we're going to concentrate on the chemical senses. So this is taste and smell and something called mouthfeel, which is really a characteristic of what is a nervous system in our face called the trigeminal system. And that involves anything like texture, spiciness, all of those sorts of characteristics come by way of the trigeminal system. We have a limited number of senses to work with. Fortunately for us, half of our senses are chemical senses called chemosensing. Primarily among those are taste and smell and something that in beer we generally refer to as mouthfeel, but that's actually coming through a nervous system in your face called the trigeminal system. So it's technically generally called those are called trigeminal sensations from your mouth and also from your nose. And then vision is another obvious sense. It's very dominant. And really the struggle in tasting is to try and ignore your eyes as much as you can because they can be pretty deceiving. We tend to follow them wherever they go, and we don't want to do that because we're trying to be objective here about these things. And then finally, even hearing makes a difference because the brain uses some of the same regions to process audio as it does to process flavor. And so there can be a competition for resources, so loud noises and things can actually be a little bit problematic for tasting. Why do we chemosense? Well, this goes back to the very beginning of life on Earth 3 billion years ago. There isn't a creature on this planet that does not have a chemical sense. And these are used for keeping ourselves alive, primarily to find sources of nutrition in the environment so that we can move towards it and recognize sources of danger in the environment so that we can move away from. These are very important things. In fact, even in bacteria, they have the ability to do that, even without a nervous system. These chemical senses are very useful for social interactions too. And in a lot of creatures other than humans, although we do it too, their social life is driven very strongly by their sense of smell. And we can recognize enemies, we can recognize potentially suitable mates. There's lots of other characteristics about smell and those social interactions. And even in humans, we're subject to those same things. There's a common sense with tasting, and especially with the sense of smell, that we're not very good at it. And the thing you really need to know is that we're much better at it than we think we are. And they've done a lot of scientific studies on that, and people actually can get down on their hands and knees and they can track a chocolate-soaked rag across a field, waving their nose around just like a dog does. You know, with a little bit of practice, you can really learn to become pretty good at this. Don't be afraid to just go in and do it. You have an inner taster inside of you that really kind of keeps track of this stuff. And not everything has to get into the conscious brain for it to make sense to your body and to your brain. The other thing is language is really hard. A smell especially comes in your nose to some very ancient systems kind of right inside of your head that are limbic systems. So they're involved in emotion and memory and good and bad. And they're not really good at language. And your language brain is way up in the top of your brain in the highly cognitive parts of your brain. So it's a long journey for it to get there. So, you know, when I talk to groups of people and say, who feels like they don't know language very well for tasting? And every hand goes up if I force them to. But so it's not a flaw, it's not your fault, it's just the way you're structured, you know, because again, tasting is a function of, should I go towards that thing or should I move away from that thing? That's really the purpose of it. And if you understand that, it all makes a lot more sense. Over time, there are things that experts do to develop specific expertise, to learn a language that's shared amongst aficionados of wine or beer or whatever, and practicing tasting and familiarizing yourself with this vocabulary and with the particular chemicals not only changes your mind, but actually can change your nervous system in a way that rewires it so that you're more competent. So in addition to the senses, we have a number of characteristics that we need to evaluate that are a little more intangible. And these are things like depth, complexity, balance, harmony, characteristics that adhere to a particular style, which is really important when beers are being judged in competitions. So these are sort of a secondary set of characteristics that you also need to learn to deal with too. It's a little bit of an abstraction of the basic flavors. So as a taster, you learn how to take the inputs that are coming in terms of smell and taste and sort of translate them into this secondary language. We have a number of psychological tools that we can use in our kit to become better tasters. One of the things is that hedonics, that is like and dislike, is a very fundamental characteristic of all of these sensory systems, these chemosensory systems. So just paying attention to whether something's pleasant to you or whether something's unpleasant to you can be really important. And of course, over the course of your lifetime, you bring a whole history of your experiences with these flavor characteristics in terms of memories. And these can be super rewarding and super important and really a very valuable tool because as you've experienced, I'm sure, one little smell, brief smell can put you into a kind of a rapture state where you're all of a sudden vividly in an ancient memory. The famous story in the Marcel Proust book where he takes a bite of a cookie and goes on for hundreds of pages about the memories that this triggered of his childhood. We live that every day. And those are really useful to us for reasons I'll explain in a minute. The other thing is that we're very responsive, that all of these chemical sensory systems are highly responsive to attention. So when you're tasting, having your mind focused, having certain expectations of what you're trying to look for, maybe thinking about the hops in one sniff and trying to understand those, and then maybe the next sniff and the next taste, you focus a little bit more on the malt or the yeast character or whatever. So our brains have a kind of an internal searchlight on them, and they will focus on whatever you need them to. So be aware that you have that as a tool to kind of really put your tasting energy where it needs to be for whatever you're trying to do at that moment. And then of course there's training and practice. Your nose actually physically changes its characteristic as it responds to different chemicals. So if you were to move from the city to the country, in a couple of weeks you would have a whole different population of olfactory receptors because you have different things to smell in the country than you do in the city. And the other thing is that experts in any area, they're not any more sensitive to any of these chemicals than you are, really. They just know what they're looking for. They know what to expect. And so that's a big part of it. And they know how to talk about them so that other people can understand them. We tend to think in these memories and tend to think that something will remind us of banana candy, for example, or whatever. But we need to, in the wine world or the beer world or the perfume world, you need to know that language. And that's a big part of becoming a professional. Chemical senses are a pretty big part of us. In fact, olfaction, the sense of smell, is 1% of our entire genome. It's the single largest chunk of our DNA in our whole DNA. And if you think about 1%, doesn't seem like much, but a chimpanzee is 0.5% different from us. And if you think about how, like, that's pretty different. And so, you know, this is a very powerful part of our DNA, which really indicates how important it is to us. And as a result of this different DNA, we all have different sensitivities to different chemicals. Because of the way we sense chemistry, everybody has a slightly different point of view on them. And some people have super sensitivity to certain chemicals because they may have extra copies of receptors for them. Some people may lack receptors for certain chemicals. So there's a lot of individual differences, and you have to learn what yours are. That's another part of learning the tasting process, is learning to know where your strengths and weaknesses are. The other thing about smell is that while smells have a hedonic character, that is an inherent goodness or badness, in humans, those are not hardwired. Those are acquired. Whereas mainly in taste and in the trigeminal system, our positive or negative feelings about things like sweetness or bitterness, we come pre-wired with those as children, and we can modify those a little bit. But with smell, it's all up for grabs. So you may have seen this tongue map in school, in grade school or high school or something. I'm not sure if they're still showing this to people, but this is an amazingly long-lived yet incorrect phenomenon. But if you look at the actual structure of your tongue and where taste buds reside, this old map really has very little to do with reality. In actuality, you have 3 separate areas of the tongue that are sensitive to taste. All regions of the tongue contain little bumps. Some of the bumps have holes in them, and inside of those are taste buds. And so those little pores at the top of these bumps allow the chemicals on your tongue to get in and reach the cells that have the receptors for taste. Those taste buds contain cells from multiple different kinds of tasting receptors. So on the front of your tongue, they're really equally sensitive to sweet, sour, salty, bitter, and umami. On the sides of your tongues, you have another couple of sets. They almost look like little shark gills back at the back of your tongue. They're a little bit more sensitive to sour, but they also are sensitive to all the other flavors. And in the very far back, you have another group that is just right at the back of the tongue where water falls down into your throat. There's little round circles of taste buds in there, and those are more sensitive to some of the more complex flavors like sweetness and bitterness and umami. And they're actually wired into the brain a little bit differently in ways that we still don't understand. So this is why with beer, as opposed to wine, that we generally like to swallow the beer when we taste it rather than spitting it out. And of course, beer's a little weaker anyway. But having that bitterness reach the very back of your tongue, it gives you an impression of the bitterness that's a little bit different than you have in the front. But in terms of like sweet, sour, salty, bitter regions in the tongue, that really isn't the case. We have taste buds all over our tongues, and they respond to different chemicals. We also have them on the insides of our cheeks and in our gums a little bit down our throat, not too much. We also, weirdly, have taste receptors, that is sweet and bitter receptors in our nose, right in the same areas that our olfactory receptors are. And these play a role in detecting dangerous bacteria and squirting out toxic chemicals to the bacteria as a first line of defense, which is really pretty interesting. And further, you have taste receptors all through your body, in your reproductive organs, in your gut, especially, where they do a lot of work of understanding sugar levels and recruiting release of hormones and digestive enzymes and things like that. This is a really mysterious area of science, and they're learning a lot about it, but there's still a lot they don't know. But taste is widely used for many other purposes beyond what we're going to do to taste a beer. Another really interesting thing is that you have a microbiome in your mouth and microbiome in your gut. And those bacteria are capable of sending sweet and bitter and other kinds of signals to tell your brain what it wants. And so it's really interesting to think that we're kind of hijacked by populations of bacteria that talk to us and tell us what they want us to do for them. So in bacteria, the sense of taste, it's actually really more of a sense of smell in the way it works. But in bacteria, these receptors are connected directly to the little motors that propel a bacteria forward or backwards. And so this is where the hedonic nature, this value, this quality, good or badness of chemicals comes into play, because in a bacteria, they can directly manipulate their bodies simply based on the chemical sensations they're receiving from their environment. And it's the same for us. Should I eat this? You know, and our sense of taste actually is wired in early, comes directly into our brainstem. And if something is really awful and tastes really bad, then we don't have to think about it. We don't have to get our brain involved at all. And our brainstem can recruit motor neurons to tell muscles to spit it out, choke it up, or back away from it. We have two main kinds of receptors respond to chemicals. And again, there's only, you know, a handful of chemicals that we need to respond to. The first group are that we use for tasting salt and for tasting sourness or acidity, pH actually. And because these are relatively simple mechanisms, they can act really fast. But the second type of receptor is used for bitterness and for sweetness and for umami. And this is a much more complex reaction. These receptor cells kind of have multiple stages where chemical will trigger a change in a receptor, and that will trigger this whole cascade of chemicals coming in and out of the cell and eventually trigger a neural impulse. And they look a little bit like pinball machines, honestly, because there's so many little steps and stages in there. And the reason that's important to know is that they're called G protein coupled receptors. And the reason they're important to know is that they work a little more slowly. So as salt might get a just absolutely blazing fast reaction to us, whereas with umami and sweetness and bitterness, there's a little bit of a delay in there. And that's really important when you're tasting, is to consider tasting as something that has a timeline to it, that it's not one thing frozen in a moment. It actually has a beginning, a middle, an end, and an aftertaste. So it's always really important to think about that. Taste is very much hardwired. You know, if you put sweet liquid on a baby's lips anywhere in the world, newborn, love it, love it, love it. And bitter generally gets a kind of a dubious or rejection response. Think about kids and broccoli, right? But we can change that. Obviously, all you IPA fans out there, you've learned to like bitterness. You know, bitterness is a bit of a mystery. We'll talk about it in a second. Each of these tastes has a kind of a characteristic response curve, and especially with sweetness and saltiness, there's what food scientists talk about as a bliss point. Whereas a little sweet is good, and you put a little more sweet on the tongue and it gets better and better, but then it gets to the point where it's kind of too sweet, and our liking for that kind of falls off. And it's true with salt too, that a little salt's delicious. The right amount of salt is just fantastic, but too much salt actually will trigger a complete rejection response. So it's important to know that they're not just a linear response. They're kind of a weird curve that you can definitely get too much, even of a good thing. The bliss point of sweet is not a fixed point either. And same for salt, that these are modulated by our body's needs. We have a system in our gut of hormones called leptin and ghrelin, and one of them is a hunger hormone and one of them is a satiation hormone. And when you are hungry, one of those hormones makes sweet and fatty things taste really, really good to you. And when you get full, they just don't taste as good. This is why, you know, you start out on a big meal and man, that beginning, those first couple of bites are just fantastic. And then after a while, you get a little full, the insulin's starting to pump, you're getting kind of filled up, you're getting a little bored with the flavors a little bit even. And part of that is because your brain is just like not as interested. With smaller animals like mice and things like that, they can literally not even smell the food if they're full, because those systems just automatically kind of shut down for them. But humans, we can do that. And each sense is specific too. So sweetness has its own satiation thing. Salt has a different one. Bitter, you know, you IPA guys, you can never really get enough of it. And it's not really a chemical that we need to survive. It doesn't have the same kind of response curve. One interesting thing about artificial sweeteners is two things. One is that they never quite reach the bliss point. So artificial sweeteners and like colas and things like that are close to, but never hit that bliss point. So people are always a little unsatisfied with the flavors of them. And the other thing is that artificial sweeteners will actually trigger the same kind of insulin release in your gut that actual sugar does. They'll release a bunch of insulin, but then there's nothing for the insulin to work on. So they can really kind of create a lot of havoc inside your body. They're not really as benign as you would think they are. Sour things, we get a kind of a, well, I don't know, let me see about that kind of response to them. So hedonically, they can be really fabulous. They're great counterpoints to sweet things. They're generally, I think our body recognizes them because they're sort of a marker of whether fruit is ripe or not. And that sourness in an unripe fruit is an indication of probably not much sugar value there, not much nutritional value if it's still unripe. And probably that's going to come along with a lot of harsh, unpleasant tannic and polyphenolic material that's just not that much fun to eat. Acidity, it's just another early warning for that. And sourness, in addition to being a taste, also can be a trigeminal stimulant. It's fairly common with a lot of types of chemicals, which means that you can go from having an unpleasantly high amount of sweetness to actual pain created when these acids start to kind of attack your cells that are hooked into your trigeminal system. So it's another kind of backup system for avoiding dangerous things. If you've done a lot of brewing and especially worked with sour beers and stuff, you might have heard that acidity in beer is not very well measured by pH. Of course, pH counts the number of hydrogen ions, and that is true, it measures those correctly, but it turns out that different types of acids, different chemicals that are acidic, have different amount of access to those receptors. And so an acid like citric acid, even though it's not as sour as a mineral acid like hydrochloric, on a pH basis, it's much more sour. Acetic acid is also more sour than hydrochloric or nitric or one of those acids on a per pH basis. Salt is really to keep your body's balance of salt in line. If we don't have enough salt, we will die. That's a really, really important thing. And we actually have two different systems with completely separate receptors. One is an appetitive system that is driven by the salt level measured in our brain by some salt receptors in our brain. And when we're depleted, salt tastes good. When we're not depleted, it doesn't taste that good. And we also have a second completely separate system that's wired differently with different receptor cells that's basically a high salt alarm system that goes off and causes you to kind of, do that rejection response and stick your tongue out and gag it up. So like if you've ever accidentally put salt or had the salt shaker lid come off on a thing and you bite into that, it's like, ah! And you make this face. And that is the rejection response. That's an unconscious, autonomic thing that your body is doing to help you out to expel that food out of your mouth. Amazing. So bitterness is also kind of a warning system. It's always been thought, and every paper that talks about bitterness says, of course, we all understand that bitterness is because a lot of poison is bitter, and so that's our system for detecting bitterness. But really, if you look at what chemicals are bitter and what we can taste and how much those bitter things we can taste are poisonous, it turns out that like half of all bitter chemicals are not poisonous at all. Hops, for example, not the least bit toxic. We love hops, despite the fact that they have a ton of bitterness. And if you look at a list of toxic chemicals, half of toxic chemicals aren't bitter. And all the deadly ones, cyanide and some of those kinds of things, they're not in any way bitter. None of those are bitter. So it's always a bit of a mystery. I have a kind of crazy theory that bitter equals medicine. And if you look at the Chinese and the Ayurvedic traditions of natural medicine, they judge effectiveness by how bitter things are. If you look in the wild, gorillas and chimpanzees will pursue eating bitter plant materials to cure certain things like diarrhea in the rainy season or things like that. So there's a thing inside of us that's sort of like, well, we don't like bitterness, but we're kind of interested in it, and I think that's proves that that rings true for hops. That people are like, well, that's interesting, but I don't know, it's kind of bitter. And then after a while, you just get used to it. And then, of course, you learn to crave it. The other thing about bitterness is that it's a little slow to act. And part of this is because it's part of that G-coupled receptor system that's just a little pokey. But the other thing is that it's not only a little bit slow to act, it takes a while to really build up to a full intensity. And also, it takes a very long time to leave your tongue. And that is because bitter compounds tend to be hydrophobic chemicals, which means that they are water repelling and generally kind of fat loving compounds. And those type of chemicals think of them as like waxy, greasy, just like hop resin, right? Those chemicals tend to just get on your tongue and stay there, right? They get on that flesh of your tongue, and those fatty chemicals really like to be on flesh. And so it takes a while. I've been at a beer event and had a big double IPA, West Coast IPA, and driven home, and a half an hour later, I could still taste the hops. And that's because of the nature of those chemicals in the hops that are the bitter compounds, that they're waxy, and they just get on and stay on. The other thing about bitterness is that it's very complex in terms of its cellular structure, right? We have 26 different chemical receptors for the taste sense of bitterness, which is far more than anything else. I think there's maybe 3 for sweetness, and the 2 different ones for salt, and then just 1 for sour. But bitterness, we have 26 different receptors. We don't know why we have so many. Bitterness is widely conserved across almost all animals. If you think about, like, cats cannot taste sweet because they eat meat. They don't need to taste sweet. There's no use for it, but they need bitterness for something. We have these like large numbers of receptors. And you would think with 26 different receptors that there might be different bitter chemicals that could cause somewhat different bitter sensations. And I will say that, like, for my money, the bitterness of hops is a little softer and nicer and cleaner and friendlier than that bitterness that you get from wormwood. But the science doesn't really back this up. And maybe it's just because they haven't really figured this out. They don't really know how we don't know how all those 26 signals get combined into the brain. So it's a bit of a mystery for us. So about 20% of the population is extra sensitive to this family of chemicals that are found in vegetables. There's one chemical called prop that you may have done an experiment in high school where they pass around little paper strips and you put it on your tongue, and 20% of the class is like, oh my God, this is so horrible, get me some water, I can't stand this. And another 20% is like, what are you guys talking about? I don't get this at all. And the remainder of the room is like, well, okay, I get a little bitterness, but it's nothing bad. And this is just this genetic variation. And it turns out that this genetic variation, they call it super tasting. It's not really the right word for it because it's super tasting for something very specific. But it comes along with a lot of other different characteristics that they may have a little bit more aroma sensitivity. Super tasters tend to be more interested in sweet things than other people. Like the people that I know that are my friends and family that are super tasters, they tend to like sweet things better than the rest of us. They drink sweet wine if they can get their hands on it, or sweet beer like a fruity Belgian lambics that are in the market. There's this variation. And again, it's a simple little test. You can take it yourself and see where you're at. But it informs your choice in beers. Obviously, people who are super tasters, not big fans of IPAs. People who are super tasters tend to really not like red wine very much because they perceive those tannic compounds in wine as being kind of bitter and unpleasant and on that same spectrum. So if you've always wondered about why are you like this, or why don't you like red wine, there's maybe your answer for you. Oh, and I should say that this super taster phenomenon is a little bit more skewed to female than to male. Not dramatically so, but there are more women that are in this category. So now we get to the weird ones. Umami, as a term you probably have heard in connection with cooking. It is basically a sensitivity to a amino acid called glutamic acid, but specifically in the form of a salt called glutamate. So if you know what monosodium glutamate is, that is the chemical that this system really works on. It is described basically as a kind of a meaty, brothy, rich, proteinaceous kind of savory flavor, but it only functions that way when it's paired with the right aroma compounds. Because if you put it by itself, it really doesn't taste like much of anything. And if you put it with something incongruent, like a rum flavoring, for example, somebody did an experiment on, people just hated it. It was awful. But if you put it with the vegetable characteristics, like smells of vegetables, smells of meat, then umami just turns into the most glorious, wonderful thing. And the big fad for udon that's out there right now, where people really want that bone broth and that rich flavor, that's really all about the umami. And in addition to umami and the glutamate, there are a number of other chemicals called ribonucleides that also have umami boosting characteristics, and so they reinforce one another. And chefs actually play games with these things and use mushrooms and rich stock and seaweed and tomatoes and all kinds of other things to sort of pile on these umami flavor to create this very rich, umami-rich food that's very popular in nicer restaurants these days. And there's another one that's even more subtle, and it's almost impossible to detect it itself. It only makes things that are already taste pretty good taste even better. It's called kokumi. And the best way it was described to me is, imagine a stew pot that's been sitting on the stove all day, and all these flavors are all mingled together, and they're creating this rich, brothy, meaty mouthfeel, and that's kokumi. It's important in food. Neither of those two things are particularly players in beer, although in a really old, maybe 20, 30-year-old barley wine, you might get a bit of a soy sauce character from yeast that's fallen apart and released a lot of its amino acids into the beer. But other than that, it's not. But it's really important for beer and food pairing. So if you do a lot of work like that, you want to really get familiar with it. And also, just like, it's good to know. But it's easy to ignore. You know, one study, they looked at people in Germany, and like only 5% of people in Germany had any idea what umami was, despite like German cuisine is super rich and gravy and all this other stuff that has a lot of umami, but they're just not like thinking about it. So it points out the importance of awareness and focus and things like that. And there's more. We can actually taste starch a little bit. Our taste buds will start to degrade starches into sugars, but it's not quite clear that that's happening. But we do seem to have a receptor system that allows us to taste dextrins, which are these chemicals that you find a lot in beer. It's a lot of the starchy residue in beer are dextrins, and they're not huge like starches, but they're not tiny 1-2 sugar units like sugars are. They're sort of intermediate. And we can recognize those and taste those. So there's a character there, although it's hard to notice. You know, it's not like sugar or bitterness on your tongue. It's more subtle. Metallic flavors also, like zinc and copper. If you've ever used those, like tasted those zinc lozenges that they use for colds and things like that, you know, they have this weird, dull, I don't know how to even explain it, metallic taste, let's just say. Like lick a penny, you get a particular metallic kind of characteristic. Iron, we respond to iron too, but it turns out that iron goes through a reaction and creates another chemical that is aromatic. So iron we generally smell, that sort of bloody smell, like bloody nose kind of smell if you get a little iron in something, like in some well water or something like that. That's actually an aroma. So there's a neat little trick. If you ever think you might taste some iron in a beer or in water, take your finger and take a little dab of that liquid and put it on your skin, because your skin contains the enzymes that will create that chemical reaction to make that iron smell, and then you can sniff the back of your hand. So if you're taking the Cicerone exam, that's a really good little trick to know. We can also taste fat, specifically free fatty acids, but you don't really have an impression of that. It's believed that those signals go from your tongue directly into parts of your brain that manage your metabolism, and there's no need to involve us in that process. So we sense fat in a more of a pedestrian kind of manner, I guess you'd say, by its slipperiness, right? It's called the sliding coefficient of friction. Like, think about an ice skate on ice versus an ice skate on sandpaper, right? That smoothness, that's what's going on in your mouth when you have, like you're eating fried chicken or you're eating ice cream, that creaminess. And we're really, really strongly wired for preference on that, obviously. Those are great flavors. You know, you get them in lots of different kinds of foods, especially in dairy and desserts, but also it's a very desirable characteristic in beer. It's one of the appeals of the hazy IPAs, is to have that rich, creamy palate, because again, that's a pleasurable sensation for us. So it's worth understanding how to produce that. So now let's talk about smell. This one's complicated. We have 391 receptors. This is this big hunk of DNA that we have. 391 different chemical sensors to detect different kinds of chemicals. Dogs have 93 million, I think, and humans have far smaller number than that. But despite that, we're actually quite capable. And interestingly, humans have more copies of receptors, of a lot of receptors, than animals do. It's cool to think about like that bears and dogs can find a dead, rotting meat a mile away. But obviously we don't need to do that. But we know when the French fryers going at McDonald's, you know, from the car. We can smell that. And so, and a lot of these multiple copies we have are very much fine-tuned towards foods. Again, we have superpowers. They're just different superpowers than those other kinds of mammals. Now, these 391 receptors are combined together into what's called a combinatorial scheme, right? So on any given chemical, you might have, I mean, there are some receptors that are only sensitive to 1 or 2 chemicals, but there are other receptors that may be sensitive to hundreds or maybe even thousands. They don't know. This is something they're still working out. They're still working this out because it's very complicated to study, very difficult, and they're making progress, but it's taken a long time. Every time you smell, your brain gets presented with a pattern of responses from these receptors. And the chemicals actually fight with each other for spots on the receptors, right? So there's this battle going on for binding, and they bind and create positive sensations, and they bind and they create negative sensations. And all of these things get transformed into more or less like a picture. Think about dots, light, dark, big, small dots, all kind of presented to your brain. And we use processes in our brains that are similar to the way we decode faces, right? So once those signals go out of your nose and into your olfactory bulb, then there's one nerve, one set of nerves that go from the bottom to the top. And by the time they get out of there, they have transformed that picture from the pattern of receptors into a pattern of characteristics that may include, do I like this? Is this like fruity? Or is this, you know, and again, we don't know exactly what that part of the brain is like speaking to the other, what language is using to tell the other parts of the brain. But that transformation happens really rapidly. It's really interesting. So that means we really have that ability to taste, to smell really anything. There's no real limit to it. It's estimated that there are billions of smellable molecules. We don't really know them all. Any chemical that is of a right molecular weight and right volatility should be smellable. So how many aromas can we actually smell? Like if you start putting different chemicals together and make a perfume and stuff like that, how many smells? Well, somebody did a study. They came up with like a minimum of a trillion and maybe 1,000 trillion, but the math wasn't good. People didn't like that answer. So right now we just don't know. It's almost infinite. You know, you think about 391 receptors, billions of chemicals, like what are the possibilities? So for any reasonable purpose, it's absolutely unlimited. To simplify things a little bit, fortunately, there are about 10,000 different odor molecules involved with food. Of those, a small subset, maybe 1,000 or so, are involved in like make the difference. And there's 16 molecules that are found in 25% of all different kinds of foods. All of these molecules that are really relevant to a lot of different foods are called key food odorants. And human beings are super sensitive to foods for obvious reasons. And we actually have sensitivities to all of those kind of cooked, caramelized flavors, the flavors of cooked food. And that's really been within the last 1,000,000 or 500,000 years of our development that we've acquired the sensitivity of those molecules, because rats and mice can hardly smell them at all. Women generally are a little more sensitive than men to smell. And one interesting thing is if you look around at craft breweries and the people who are running the sensory programs in those craft breweries, by and large, they tend to be women. For whatever reason, maybe not just because they're sensitive, but because it's a job that women tend to really do well and gravitate towards. I can't explain it necessarily, but I think it's really interesting and very cool. Our preferences for smells are mostly acquired. We have some general dispositions about them, but generally we learn those things over time. If a smell that we find that we now think of as pleasant, it may be because it's been associated with a taste for which we do have a strong preference, like sweetness. So there's a number of things like vanilla, for example, that are invariably associated with sweet things. So people find vanilla very appealing, and that's really just learned behavior based on what we've been eating and drinking for our lives. Now, as we get older, especially when you get into your 80s, your sense of smell is definitely declining, maybe noticeably. There certainly are disease conditions around that can cause that to be diminished. There are some interesting implications in depression and other psychological conditions that people sort of suffer a loss of impact of smells and tastes. And you may have heard of people that are driven mad by the smell of carpet or paint in a room or things like this. And these you might think are super smellers. What the evidence really bears out is that they're not really super smellers, they're super noticers. And that in general, there's not a mechanism to provide a high amount of overall olfactory sensitivity in our systems, because the genes are all in different places and there's no way 391 genes would all be overexpressed. So there's something else going on with the people that are really focused on these environmental smells to the point where it really causes them a lot of problems. With the combinatorial scheme, you may have the same receptor that can couple to a lot of different molecules. You may have the same molecule that can couple with a lot of different receptors. And again, this presents this pattern to the brain that the brain decodes. And it used to be believed that these were lock and key kind of things, that one receptor came in and just like fit like a glove with a receptor and that triggered the thing. But it turns out these like parts of the receptors, they call them pockets. And they're just sort of loose dish-like affairs where the chemical and atomic and electrical charge and other characteristics of a molecule just happen to like find a home in this little pocket on the protein on the outside of a cell. And when they do, that changes a characteristic of the receptor on the inside of the cell that starts this whole cascade of activity that eventually results in a nerve impulse. Now, the interesting thing, I think, in terms of like the way we perceive smells is that because we use pattern recognition for this, there's an aha moment, right? And so if you think about, you're walking down the street, you see somebody coming a block away and you think, hey, I don't know, do I know that person? And there's a point where you get to the point where you can actually see the face and it's a friend, and you just have that instantaneous kind of recognition. And that's the way smell works too. That sense of familiarity. First, it's just this pattern, it doesn't make any sense. And then you finally connect that pattern with a stored pattern in your brain under the control of your hippocampus, which is your like memory storage system, and bam, there you are. So it explains that kind of characteristic. So you're always searching, you know, with tasting, it's always like, what am I getting? What am I getting? What am I getting? You know, you got to let those little memory things help you out. The olfactory system behaves in a way we call plastic. And that just means it's really adaptable. And this happens in a lot of different ways. One is we just acquire memories. And it's almost like a system of filing cards in our brain. You know, when we smell chocolate, like we know chocolate, we know when we eat chocolate, so we know like the context of chocolate. We know that like we like it, so there's a positive hedonic value to it. We may have some details on it, or if we're a chocolate expert, we can tell if it's African chocolate or South American chocolate, or how old it is, or how it's been processed. So we control the characteristics that we attach to these smells. Part of our training and learning about tasting is learning to manage these card catalog that we have and add more information to it. This is a big part of wine training. When they train sommeliers, they train them by grape, by region, by vintage, by vineyard, and they learn more and more and more subtle characteristics that they attach as little index cards to those particular aromas when they find them in the glass. We do adapt our nose to different environments too. By actually practicing and tasting samples of chemicals, maybe beer off flavors or something like that, we learn those chemicals, but not only do we learn them, we actually sort of grow more receptors for them. This part of your olfactory epithelium and the olfactory bulb are just a few of the places in the brain that actually create new cells throughout your lifetime. And as you get older, your production of new cells kind of winds down. And so there are less of these new cells created, and that's one of the reasons why smell diminishes. And there are other conditions like dementia, like Alzheimer's, and particularly Parkinson's, where a loss of smell is like the earliest warning sign that they know of for those conditions. So there's a sequence. The first thing that happens is the aroma molecule hits that receptor, it locks up, it goes through this whole transduction event, it sends a cellular signal, that signal goes up and goes to the olfactory bulb, it mixes with others of its kind, it gets clarified, processed, imaged, enhanced, like all the things you might do with an audio signal. Those are all going on in the olfactory bulb. And then it gets up to a little bit higher level, and you're understanding, do you like this or do you not like this? That's something that happens pretty early. Then you get identity, so you kind of know what it is. And then at some point, you can get the whole context and really recall a memory and have a full understanding of what it is you're tasting. So here's an image of a cutaway head. You can see the oral cavity and the esophagus, nasal cavity, and there's a lot going on in there, just in the anatomy, right? In addition, we're overlaying 3 different sensory systems onto this map: taste, smell, and trigeminal, which happens both in the mouth and in the nose. So there's 2 aspects of the trigeminal system. Those get wired into the brain. All 3 of those systems get wired into the brain really differently. What's interesting about the sense of smell is that unlike all of our other senses in our whole body, smell is wired differently. It may be partially because smell is the very oldest chemical sensing system. Like, it goes back to when there weren't even bacteria. There were these things called archaea that came before bacteria and lived 1 billion years or more. Part of that may be the reason it's different, but the other thing is every other sense goes through something called the thalamus. And the thalamus is involved, like vision goes through there, sound goes through there. Everything that goes through this thalamus has a precise location and timing. And so the thalamus is kind of keeping track of your environment and what's going on around you and your environment, and doing a lot of the calculations that help you maneuver and control motors and control language and control speech, actually, and things like that. But aroma, smell comes right in. It goes into these really ancient parts of your brain. It goes directly into the amygdala, which is like the house of pain and pleasure, which is really like a very highly emotional center. It goes directly to your hippocampus also. Well, not directly. It goes through another couple of little units to do some processing, but they wind up in those centers. So smell has an impact on you and a feeling. It presents itself in a just different sensation than other senses do. I think that's important to understand. And as the signals from your chemical senses converge, and they converge first with each other, and then they start to converge with hearing and sight and everything. And every step they go a little bit higher, they blend together, and so they become kind of multisensory. They merge in ways that's sometimes really difficult to pull apart. It's another thing we kind of need to look at. And eventually you get all those things up to your thinking brain, up to your cognitive brain up here, at which point it's all sort of like completely integrated and multimodal, and they're all talking together in a language that we don't quite understand yet. That's generally structured. And what happens is that these higher, there are loops and loops and loops. And so every time a signal goes up, there's also signals coming back down to pre-program these lower levels so they can be responsive, to take action, to respond quickly, to make quick identifications without getting the whole brain involved, because the whole brain is limited in resources and kind of slow compared to what can happen closer to the source. So there are 2 kinds of smelling. This is really, really important. Can't overemphasize this enough. The first kind of smelling is called orthonasal. So if you look at the cutaway, you'll see the arrows coming in from the front of the nose. That air is coming in a particular kind of airflow, and that is contacting the receptors that are up inside the back of your nose up here, kind of in where you put the swab for your COVID test. It's that area. And so when the smell's coming in from the front, your brain knows that, because your nose knows which direction the breeze is blowing, and it flips a switch. And so the orthonasal is more sensitive on any given chemical. It can detect it at a lower level. It's also more kind of evaluative. It's more analytical, I guess you'd say. Even though it's a lot of emotion and hedonics and everything, it's still like this is your more analytical part of your smell system of smell. And it's more a sense of smell by itself without being meshed together with taste and mouthfeel and other things. Now, when you smell the other way, it's called retronasal smell. Retronasal smell is for things that are already in your mouth, things that you maybe probably have swallowed already. So it tends to be much more focused on food. The retronasal uses the same set of receptors, but since the brain knows that the air is going out of the nose rather than in, it sets up a network of neural systems that's somewhat different. So it's more about familiarity. It's more about preference. It's more about, I'm feeling like mom's home cooking. rather than really breaking it down and analyzing the other things. And it also presents your brain not really just with odor, but with something we call flavor. Now, flavor is a word that's sort of widely bandied around, used sometimes interchangeably with taste, but it's really not a sense at all, but it's a sort of a synthesized sensation. It feels like a sense, but it's really a sense composed of 3 other senses blended together: taste, mouthfeel, and again, it's already been in your mouth. It's familiar, unfamiliar. It's probably not going to be poison, so it's not really looking for things that are particularly bad. Now, there's one really interesting thing about retronasal, and if for no other reason than this alone, you should always be doing it. We'll talk about technique in a bit. But retronasal, because it's in your mouth, because your mouth is full of all kinds of enzymes from your own saliva and also from the population of bacteria lives in there, they're capable of breaking down molecules a little bit, busting them up. And there's a group of molecules that are called glycosides. And glyco means sugar. So there's a sugar involved. So sugar is like a ring, a 5 or 6-sided ring with something stuck onto it. And in the case of these glycosides we're talking about, what's stuck onto it is an aroma molecule, right? And aroma molecules have to be light so that they can volatilize up and reach your receptors. But as long as they're stuck onto a big, heavy, carbon-rich sugar molecule, they aren't going anywhere. And it's estimated that 70% of all wine aroma is actually bound up in glycosides, right? So people who make wine are actually looking at using glycoside enzymes to break those bonds during fermentation to liberate some extra fruitiness. And we're starting to experiment with that here for doing some fruit beers and things. And I've even seen some things where people are looking at glycosidase enzymes with hops to release hop aroma compounds, because hop aroma compounds also have a lot of glycosides. And so you're literally, when you're smelling that in a retronasal way in your mouth, after those aroma molecules have been released from their sugar chains, you're smelling things that literally were not in the glass. Like they could not be smelled through the front of your nose, now you're smelling them through the back of your nose. So you're going to have a shift. Maybe things are going to feel more fruity because they typically tend to be a lot of fruity molecules because fruit produce them. It's like part of what fruit do is they bind all these ester molecules into glycosides during their production. I don't know why, but they have some purpose for it. That's a really interesting thing. And the other little tidbit there is it's a really good idea not to brush your teeth within an hour of doing a critical tasting, because all toothpaste has antibacterials in it. And if you brush your teeth, you're going to kill that population of bacteria, and it takes a little while for it to grow back. So not to mention that fresh minty taste is really kind of off-putting when you're trying to taste beer. One of the reasons that aroma is so hard for us is that we don't have what's called a semantic structure for it very well. And a semantic structure, if you think about a rainbow and light, it's pretty simple. It's like take a prism and shine sunlight and it just gives you this spectrum. But that spectrum is actually created in our heads from a combination of red, green, and blue sensitive receptor cells in our eyeballs. And so we have a sensory system that decodes a very simple electromagnetic phenomenon that has a characteristic called wavelength, and we interpret wavelength and make color out of it, right? So light is really, it's a physics that just like it starts at red and it ends at violet, and that's really pretty much it. We don't have that with aroma. We struggle a bit with it because we have a hard time putting it all together on one big map. And everybody has done flavor maps. I've done them. The famous Morton Mildgard beer flavor wheel that was done in the 1970s. There are newer versions of different kinds of beer flavor wheels. But the more universal you try and get, the more difficult it is to make a whole wheel that really works together without having big gaps and weird discontinuities in it. The more specific you are, the more successful they tend to be. So one of the things you should get familiar with as a taster is learn to use these circular, or they call them polar or spider charts, that basically arrange everything in a wheel. And then, like for example with hops, you know, it's fruity and citrusy and grassy and different characteristics around a circle, and then they'll plot a hop variety according to how intense it is on any one of those things. So those are good both for understanding like what other people think about, but they're also really interesting tools for you to use to understand those characteristics and do those yourself and plot those out. But just again, there's one more reason why odor is difficult, because we don't have this underlying cognitive structure that we can hang everything on. You may have noticed that if you are around a smell for a particular period of time, that you stop noticing it. This is called habituation. And habituation happens with smell a little differently than other senses. With taste, for example, habituation happens inside the cell. Our sensory systems are designed to tell us what's new and what's different. So when things don't change for a while, we have built-in systems that allow us to kind of ignore them. It's a matter of just ignoring the background and focusing on the foreground. Or think about a bird across a field. There's a little tiny bird, you can barely see it, but you see it moving and you could tell that that's not part of that background, right? Because it's these adaptation kind of processes. And you see it in vision. If you stare at that red square on a piece of paper and then you close your eyes or take the square away, then you see green. And that's just like your receptors becoming adapted. It doesn't happen in the cells with olfaction. In fact, we have processes that allow the cells to keep focusing on it, but we do the habituation in our brain. And what that means for us is that we can become habituated in our brain in a period of seconds, in a period of minutes, in a period of days, or even weeks. You know, we were working with Laverhouse one time, and they brought us out to their laboratory to have us smell some strawberry flavorings. And we walked in the lab, and like the conference room in the lab, and the whole place just had this weird, they call it olfactory white noise, where just like tons of chemicals in the air, and we just were just about to lose our lunch over it. And they were like, well, what do you think of our strawberry? And we're just like, we don't even know what to do here. And they're like, oh yeah, well, we're used to this. You know, so it's their work environment. I mean, you see it like if you're painting a room and you leave the house and you come back in, it's like, oh my God. Or the opposite, cookies. But that's completely a psychological process, not a cellular process. Just interesting to know. But you can become habituated, so it's always like important to, with tasting, give it a rest. Eat a cracker, take a glass of, take a drink of water, reset yourself, because even in very short terms, we can become habituated, and it's easy to lose track. And some chemicals, like sulfur compounds in particular, some of those really potent chemicals, we seem to habituate to them much more easily. We also habituate easier to pleasant chemicals than we do to unpleasant chemicals, because your bodies want to keep open the possibility of like not missing something that might be dangerous. So it varies by hedonics also. Now your trigeminal system includes a lot of different things. It's very complicated. It involves a lot of touch cells. It involves many different kinds of nerves. It's way more complicated than I ever thought until I started really researching it to try and figure out what's going on. Two main things. One is texture, and the other thing is something called chemesthesis. Right? And chemesthesis is a process of a chemical triggering a touch sensation. Right? And the most obvious example of that is with chilies, with hot peppers, capsaicin. So capsaicin stimulates a receptor called a TRPV1. That's a particular kind of receptor. They're all over the body and doing different things, but in the nose and in the mouth and lots of parts of the skin, especially sensitive parts of the skin, that chili will actually create, and those are heat receptors, right? Those receptors are designed to sense the temperature of objects in the environment. They're designed to sense the temperature of body. But when you put capsaicin on them, they send the same signal, but it's triggered by chemical means, right? So that's chemesthesis. Same thing is true, but the opposite for cold by mint and menthol type chemicals, right? So those are cool sensations that are illusions, but they're produced by the same actual receptors that produce real cold, effective real cold. Now the other thing, and probably more operative in beer, unless it's a chili beer, is that mouthfeel characteristics are important. So we have a really powerful ability to detect texture, right? So we can, even a slight, if you think about a good quality chocolate bar as opposed to a not very good chocolate bar, the not very good one's gonna feel a little bit gritty, even though the actual size of those things, those particles, is really, really tiny. But we can tell the difference even between really tiny and super tiny, right? So, and with beer, we can detect both that slipperiness we talked about with fat that you might get with like some of those glucans and gums that you'll find in rye and oats and other unmalted grain. So there's a lubricity kind of characteristic, but there's also viscosity. We can taste that too. And that's just like thickness, right? Think about corn syrup, you know, that's viscous. It's not very lubricating, but it's thick. And so we have both of those systems operative in there. And of course in beer, and we can also sense carbon dioxide that way too, although we do have a taste sensing system for carbon dioxide, interestingly. But we taste the texture, we can detect the texture of it through trigeminal. Now what's interesting about trigeminal is that it's really about warning. It's really, well, partially about warning. So with soft, creamy, round things, that's an appetitive system. But most other characteristics, especially when they get going in your nose, are really kind of warning signs. So, and there are a lot of chemicals that are taste chemicals and also aroma chemicals and also trigeminal chemicals, right? If you think about acetic acid, vinegar, right? It's sour, so our sour taste buds sense that. It has a characteristic aroma that's a real smell that's uniquely pickly or vinegary. And then it also, when the level gets to be high, it's an irritant, a trigeminal irritant. And one of the interesting things is that you'll quite often in beer training, you'll be tasting spiked samples with a chemical called ethyl acetate. And ethyl acetate is an ester, so it has a fruity characteristic. It's maybe a little bit like pear candy, if you've ever had that. Just sort of general happy fruity kind of chemical. But when you put it in a high concentration, it's no longer a smell. You've switched off from your olfactory system, which operates at lower quantities with this chemical, up to a much higher quantity of chemical. Your nose can't smell it at that high a quantity. It's optimized for a certain range. But now you've got a trigeminal sensation that's perceived as solventy. It'll smell just like nail polish remover because ethyl acetate is used in nail polish remover. Right? It's one of the main components of nail polish remover. It's really interesting, and it's something you have to really pay attention to, especially with those chemical kind of smells. I've found acetaldehyde will do that too. When you get it, when it's really strong, it almost comes off a little chemically. And most of those solventy chemical things kind of smell the same because it's not smell, it's trigeminal, and it has a limited vocabulary in trigeminal, right? If that makes sense. In beer, astringency, tannic structure is not all that important except for maybe in barrel-aged beer a little. With barrel-aged sour beers and stuff especially, those tannic compounds character can really provide sort of a backbone of balance to balance against the sourness and give a little bit of structure and substance to those beers. So if you're involved in tasting sour beers, especially some that have had some time in wood, do pay attention to those tannic textural kind of characteristics. There's a wine flavor wheel that has, I forget, like 19 or 20 or 21 terms for different kinds of tannic astringency kind of mouthfeel elements, but in fact, it appears that we only have two systems for measuring that. And one tends to come across as harsher and rougher and less pleasant, and the other one tends to be perceived as softer and smoother and more pleasant. So it explains that that's the kind of range that you find in wine and in beer also. The other thing about trigeminal is that instead of having a habituation where the more we smell it, the less we can smell, it actually, the longer it persists, the stronger it gets. So it operates in the opposite way, which is again indication of like what its purpose is, to be a warning. Hey, you didn't get this. I'm going to keep making it seem more intense to you until you pay attention to this and take some action. So in beer, the trigeminal sensations, you get the normal kind of palate fullness. They can be caused in part by unfermented sugars and dextrins that are in the beer that sort of make it a little richer. But most of the body in the beer is caused by a network of proteins called a colloid, which is the same physical structure as Jell-O, just thinner, right? So it produces a viscosity and a thickness to your tongue that the tongue can detect. That's why beer has that body. The other thing is this characteristic of this oily kind of creaminess or oiliness we talk about. And these are primarily done by complex carbohydrates like gummy stuff like glucans that are very prominent in unmalted grain because the malting process kind of takes a lot of that away. So unmalted grain, oats and rye, very high in that. That's why they're sticky and nasty to mash because those glucans tend to be gummy and gluey. If you think about oatmeal, you know, that's a glucan feast. But they're useful and they're important and they can really do lovely things for beer. As far as the appearance of beer, it's hugely important to consumers. And if you're sending beer to competitions, man, you better nail the color because they'll kill you for it. But in actual reality, beer color is diagnostic of nothing. You know, there really isn't anything that there's very little information it tells us. The color especially, because, you know, there are several dozen different kinds of malts that are made in different processes, and you can combine them together to get almost any kind of beer. So you can have a beer that has a very dark color, but if all that color is coming from a really, really dark malt, you're not really going to get much malty roast, any of those roasty flavors. All the light beers and a lot of the mainstream beers that are produced in this country and elsewhere have really dark malt put in them just to make them kind of gold and keep them from being too pale, because there's not that much malt in them, honestly. You're not going to learn anything from that. Clarity is style relative, so you want to pay attention to it. In a wheat beer, that's a really desirable, and in wit beer, Belgian wit beer, all of those kind of white, hazy beers, it's really important. And if you present one that's clear, it's going to tell people that probably doesn't have that creaminess that you would like. And of course, in a hazy IPA, consumers are for sure looking for it. I'm not sure that it always makes as big a difference as your eyes tell it, but as a judge, pay attention to what's in your mouth and what you smell, and kind of ignore it unless it's an important style characteristic. And of course, head retention is definitely diagnostic of a lot of different things. And you can also tell a dirty glass pretty easy just by looking at the way the beer bubbles either form or don't form on it. And if you got patches of bubbles, that's a dirty glass. So that's something you want to avoid too. But other than that, like, just try and not pay much attention to especially the color. Hearing. This is just something you would never think would be anything important. But it turns out there was a scientist who was working with mice and had a electrode wired up to part of the olfactory processing system in the brain. And he set a coffee cup down on a table and he was watching the recorder. And as soon as he put that coffee cup down, it was like, boing, it got a little spike. It's like, what is that? And so he did it again and got another spike. And it turns out that noise affects this olfactory processing. All right, so everything is really much more connected than you think. We had a thing, I was helping out Ray Daniels with the Cicerone master exam several years ago when we were at a brew pub in the afternoon. The examiners all take the same panels of spiked beers that the entrants do, you know, the candidates do. And we were sitting in this brew pub and they had the rock and roll going, you know, it's 4 in the afternoon. And we got our panels and I saw everybody like picking up the glasses and nobody was getting anything. And it's like, I wonder if that's the noise. And so we had them turn the noise down and it was like a light bulb just going off. It was amazing. So lesson, don't have a lot of crazy noise, you know, that it's distracting. And it turns out that the research shows that the higher the verbal content, the more distracting it is. And now there's another kind of noise that people are experimenting with in like a high-end restaurant kind of context they call sonic seasoning. And sonic seasoning is basically trying to play pleasant music that makes people think happy thoughts. There's some evidence that it might make sweet things smell a little sweeter. Actually, more than just like have a better experience, it actually can change the way the food tastes to people a little bit. And there's also some research to suggest that maybe in an airplane, back when they used to have food on airplanes, that it's one of the reasons airline food tastes so bad is a combination of engine noise and also low pressurization. Evidence is a little inconclusive on that, but it does seem to be. A famous researcher named Charles Spence is pretty confident that umami tastes a lot better on airplanes than anywhere else. And because he noticed the very high ordering of tomato juice and Bloody Marys on airplanes. And he did some research and put people up in the air and tested it and like got more positive results because of that. There's also a whole world of associations revolving around glassware and plate shapes and plate colors, where rounder plates make things taste sweeter and angular plates tend to make things taste more sour or more bitter. It sounds completely nuts, but the science is pretty good on this, you know. So if you're in the restaurant business, you should be careful with the color and the shape of your plates, because they can definitely have a real impact on the eating experience. And not just from a like, I like it, but from like, it's more sweet this way. Flavor is this synthetic thing, right? And what we have to do, your brain's trying to be really helpful. You know, it's trying to save you the bother of trying to analyze these things separately. It's putting them together really carefully and just sort of handing it to you. But we don't want that as tasters, right? So you have to be able to use your selective focus to understand which thing is which. Really interesting exercise is to take a piece of candied ginger, and you know, that kind of Chinese candy that's got the sugar on the outside of it. Hold your nose, put that ginger in your mouth, and taste it. And what do you get? And you're not going to get ginger. You're going to get a taste, which is sweet. You're going to get a little bit of trigeminal, because ginger has some peppery compounds in it. And as soon as you release your nose, you're going to smell ginger. And that's a real vivid demonstration of like those senses. But if you just put that piece of ginger candy in your mouth and chew it all up, it's like, oh, it's ginger flavor, which it absolutely is. But we want to know, as tasters, we want to be able to pull those apart. So you have to work at that. You have to consciously do that. And there are other weirdnesses, because we're all different, not only genetically, but in our personal history. We bring different things to the table. We have different understandings. We bring different contexts. There's social aspects. Like all that stuff is like reflected in our sensory system. So this is why judging beer and tasting in a group setting is so important. And judging especially is revealing of this. Because when you sit at a table all day with a group of other people, some of which probably know more than you do about this or have more experience, you're going to know if everybody at the table is getting diacetyl and you're not, you're going to know, oh yeah, I'm just not that sensitive to that buttery diacetyl smell. You know? So it's really useful for doing that. Now, when the large breweries bring people in for their quality control taste panel programs, they test everybody, get a baseline at the start, and then they train them on individual flavor characteristics, taste, aroma characteristics, and things that they want them to know, and train them to recognize smaller and smaller amounts of them. And then in the end, they'll put together a profile, sensitive on this, average on this, average on this, well, not so good on this. And that goes into a computer program that adjusts your scores based on what they know your sensitivities and insensitivities to be. So it's really good to get, and you could do it very informally, although it's really helpful to have other people involved. It's hard to do on your own. Although if you got a pipetter and you want to squirt some chemicals in beer, you can do that and have somebody give them to you blind and try and do it, but much more fun in a group. The other thing about chemicals is that, two things about single chemicals, is that even a single chemical will present exactly the same kind of pattern to the brain as a whole bunch of chemicals. And in fact, they're a little harder to understand for some reason. They seem more weird. And also, it also, like with, say there's a chemical called acetaldehyde, is commonly talked about as having a green apple kind of smell, but it's also like a raw pumpkin. It's also like latex paint. It's also like drunk breath, because it is drunk breath. And so there's a whole bunch of different characteristics. And it's like each of us looks at this and has a different response from our receptors, so we kind of get different characteristics. And that personal interpretation of these flavor chemicals is what we have to take in and understand and then translate to what the standard language is that's used in our profession or in our hobby, right? So that's that part of that process that you go through of learning those chemical by chemical, and they also can taste different in context too. That buttery diacetyl in a clear beer, that like microwave popcorn just comes right out, and you just like, oh yeah, this is like fake butter. But when you put it together in a dark beer, where my mind goes is pastry. Because obviously if you take wheat and make some kind of pastry that's got a lot of butter in it, you're going to have all this sort of malty, toasty kind of flavors along with a lot of butter. And so my brain thinks pastry. And so I've learned now, whenever I think pastry, it's like, aha, it's dark. Yeah, this is probably diacetyl in this. And then it's like knowing that, I can focus on the diacetyl. It's like, oh yeah, that's diacetyl, all right. And everybody else is like, oh yeah, that's diacetyl. So you learn little tricks like that. That's part of the experience. The other thing that's also quite maddening is that a given chemical will taste like one thing at one concentration, something else at another, and something else at another. There's a chemical called acetophenone, in parts per billion, it smells malty. In parts per million, it smells like tacos. And in parts per thousand, it's like Concord grape, so much so that it's an artificial grape flavor used in soda. Same chemical. Because each group of receptors has a certain range. And so the receptors that are responding to that parts per billion, by the time it reaches parts per million, that's 1,000 times more. They can't taste it anymore, so they hand it off to different receptors. And then again, at the 1,000, they're handing it off to another set of receptors. So that receptor pattern is completely different, and that's why it smells so different. Vocabulary is hard, right? Everybody struggles with it. We just don't do a good job. You got to link it to your own experience as much as you can. We're fortunate with malt because malt is cooked Maillard and caramelization flavors. And we're pretty good on those. Like we have a good culinary vocabulary to describe that. You think about bready, cracker, doughy, nutty, malty, toasty, caramel, toffee, coffee, chocolate. That's pretty good vocabulary, and that pretty much lines up with malts of all kinds. And you throw in a little bit of burnt sugar, some other different kinds of like kettle corn and other caramelized flavors, and you really got a good handle on it. Hops are tough because hops are chemicals that we don't know any of those chemicals by themselves, only maybe a little bit in citrus, because a lot of those are called terpenols or terpenoids. They're found in a lot of citrus fruits, but they're found in all kinds of herbs and pine trees and all kinds of other things. So they present this pattern, very complex pattern of unfamiliar ingredients. And in addition to that, hops have another set of very potent sulfur-containing compounds that have a lot of those fruity chemicals or fruity aspects that people are really excited about today, like the tropical and the grapefruit, the tropical, the pineapple, mango, all of those things. That's another set of chemicals. So we have, those are okay because we can connect them to fruit, but the great bulk of hop qualities, we even use a word for hops called spicy, right? It's a widespread word. It's typically the only thing people really ever say about Saaz hops is that they're spicy, but there's nothing about them that resembles any kind of spice that ever was, right? So it's just a kind of a secret code word that we use because it's like, I don't know, I don't have anything else. Let's just call it hoppy, because that's probably what it means, really. It's just we just struggle. Even the professionals use that term because they don't have a good language for it, because it doesn't connect to anything in our real life. Now, here's the trick. With vocabulary, again, you've got an inner taster right inside your head. You've got all little kinds of men running around your head doing stuff, banging on hammers, and they're taking care of business without your help. And one of them, maybe a group of them, who knows, they're keeping track of stuff that you're not quite aware of. And one of those is language. And so we were at a champagne tasting. My wife loves champagne, and I don't mind it. She picked up a glass and put it to her nose, and she goes, horseradish. It's like, okay, that's interesting, because I've got her trained not to filter herself, right? She doesn't have any particular tasting training, just hanging out with me casually, drinking some beers sometimes. But she was dead on, because I smelled the glass. It's like, oh, it's a little corky. So cork is that trichloroanisole or one of those chlorine compounds that have those musty, moldy characteristics. It wasn't real strong, but if you're thinking about horseradish, it has that pepperiness. That's a trigeminal sensation, that same chemicals that in mustard, right? So there was that, or no, I'm sorry, that's different. But that mustiness, and it also had a bit of a peppery quality to it. That was just dead on. And the reason she came up with this is because that's what her brain wanted to say, and she didn't tell it not to. And so the worst thing you can do, and every time I do a training where I have a lot of people, it's murder trying to get people to shout it out, because they just don't want to say the wrong thing. There is no wrong thing. Like whatever stupid thing you want to come up with and say, that's the right thing. Because your brain is right. Your brain's not in there trying to, what should I say? Is this the right thing to say? Your brain knows. And so you got to just not filter yourself and just let it out, shout it out. Now, the other thing that can be really distracting, and is why beer is usually, wine too, are usually judged blind, is because we have this very complex system, two systems really in our brain. One decides on valuation, which basically like how much do we like something? And we can later convert that into motivation, like liking gets converted into wanting, and wanting creates action. And we have another system in there that's our reward system, and that is fueled by pure dopamine. So when we get something we want, we get dopamine. And dopamine is just like that thing that feels really good. It's just pure pleasure. And so when we get that reward, it feels great. If we get a bigger reward than we were expecting, we get even more dopamine. And if we were expecting a reward and we don't get it, we get a reduction in dopamine, which feels terrible. So it's a kind of a punishment system as well. And also, because this valuation system works on every imaginable thing that we can think of, because it involves cognitive processes. So anything like price or rarity or untapped ratings or label art or anything and all can really figure very strongly scores that other people have given it, what everybody else is saying on Beer Advocate. You know, all of those things can really change the way you perceive those things in ways that are maybe fun and pleasurable, but they're really not very helpful to really evaluative tasting. So that's why in almost all cases, beers that are tasted in competitions and hopefully beers that are rated are generally done so blindly so that the judges and the tasters, raters, really don't know what they're tasting. Maybe they would know the style, because with beer especially that's helpful to know, because those things can be so, they can just skew the results so much. Then that's also something really important to keep in mind. You want to make sure that if you're trying to get real objectivity as much as you can, don't show people the label. Now, if you're a brewery trying to sell product, like, here's our label, here's what we're doing, you know, because it's a different thing. That's an educational tasting. You're not really trying to assign a rating, score to it, or find faults or anything like that. So it's really very much context dependent. So let's talk about practical tasting a little bit. Let's first talk about the environment. You want to make sure that that wherever you are is relatively free from distraction. Thankfully, places are non-smoking these days, so that's really good. But you want to have some decent light. You want to have the temperature be comfortable. You don't want a lot of loud noise going. If you're having a fun tasting, a little bit of background noise is fine. You don't want giant roaring conversations. You don't want to probably do one on an airplane, honestly. You want to make sure that people have some idea what they're supposed to be doing. If you're conducting a tasting, give them a little lesson. How are we doing this? How do you go through the process with them? Let them know what to expect. Give them a few hints and tricks and tips is always good. Something to write on is not a bad idea, even in a real simple consumer type of thing. A simple score sheet, aroma, appearance, flavor, aftertaste is useful. And I found out, like, when I was first learning to taste beer, I'd go into brew pubs and was writing notes. To have a little sheet that prompts you to remember to write about all those things. And those are really useful, because even if you take those sheets as soon as you're done with them and wad them up and throw them away, your brain has already processed that information through your motor sense by writing it, through your language brain, both by putting the words together, and then when your eyes, through your visual system to read them, and then back again into your language system. So it's been reinforced in multiple ways and multiple kind of pathways in your brain that makes those stronger, because each part of the brain looks at things a little differently, analyzes things differently, gives you some practice, but it also helps you understand things in a more deep way. Always a good idea to have some water available, and also a really good idea to have dump buckets. Don't make people feel obligated to drink everything that gets set down in front of them, because hopefully they will, but if you want them to, but make sure that they can move on if they don't want to. Just talk briefly about glassware. There's been a lot written about glassware, a lot of philosophizing about it. There's been some scientific research, but unfortunately it doesn't show all that much. One thing we do know for sure is that a glass that has a little bit of an incurved rim generally tends to hold the aroma in a little bit better than something that's flared outward or straight up. This glass right here is what's called the ISO glass, ISO, International Standards Organization. This is a tasting glass that's standard for spirits, for wine, for beer, for whatever. It's, relatively small. I guess it's comparable to a white wine glass. Got a relatively tall bowl on it. This is one of our beer glasses here. Similar shape, it's curved in a little bit. Anything along these lines will do. I'll sometimes use like a red wine glass at tastings just to get a rise out of people. And people are like, oh, wine glass with beer in it, how interesting. So even with that kind of thing, you can sometimes play with people's expectations. But the important thing with these is to make sure that two things. Well, one thing about pouring, I learned from the old guys up in Wisconsin. If you're gonna pour a beer, you gotta pour it. just dump it right down the middle. And what that's going to do for you is it's going to knock out some of the gas, and it's going to create some foam. So an average bubble of foam is going to be about 30, 40 times, or I think it's about 30 times more concentrated with beer aroma than the air inside the glass, right? So every time a bubble comes up, it's full of aroma, it gets to the top, it eventually releases. And so bubbles are your source of aroma. It's why champagne glasses quite often have a scratch X or a laser cut little circle on the bottom to create bubbles coming because they're pretty, but also because those release aroma. So you want to pour maybe somewhere between half and a third. You never want to fill a glass full for critical tasting because you need that headspace in there. That's going to collect your aromatics. So there's 4 steps to this process. One is the tabletop tasting. The second is the drive-by. The third is the sniff. And the fourth is the retronasal. So the tabletop, you basically pour a beer, you can swirl it a little bit, like, yeah, there we go. Can you smell it from a distance, right? What can you get at the distance? Quite often hops will come up there for you. Hops will jump out, sulfur compounds, if you've got any sulfur, if you've got any little DMS or any kind of sulfury notes, you're gonna get those. Those tend to be really volatile and they jump out and then they kind of go away. You know, it's good to start this process shortly after you pour. You don't want the glasses sitting poured with beer for half an hour before you taste it for an event. So right before tasting, and then you can always sort of, you know, put your hand on it, swirl it around. Every time you swirl, you're releasing more bubbles. There's aroma. So then the next thing is to just like do the drive-by. Oh yeah, I got a nice little hit of grapefruit in there, a little bit of maybe mango or guava or something tropical. This is a hazy IPA that was brewed down at our Columbus location in Ohio. Now I've got like a couple of things that I've noticed. So then the third thing is to get your nose in there and get a little bit of a sniff. And you don't want to do, like, if you think about a dog, how a dog sniffs, you know, they're short little sniffs. And a dog's not doing that ever, right? They don't need to. First of all, you can get everything you need in one sniff. You can go back and like focus on something else, but you get pretty good amount in the first sniff. And the other thing that's interesting to know about a sniff is that it's not just breathing, it's a neural event. So a conscious sniff synchronizes the cells in your tasting system with your respiratory system and with each other. And so there's like, it sends out a pulse of neural wave that synchronizes that system, which makes different parts of the system talk to each other more easily. So a sniff is something pretty profound, actually, when you really think about what's going on. So a sniff, think about what you're getting, starting to get a little malt. It's pretty subtle here because everything's really about the hops in this beer. Getting mostly that sort of grapefruity, maybe a little tropical, a little bit of kind of bright lemongrassy, real bright herbal notes, very pleasant. Not a ton of yeast character, not a ton of malt character. That's the smell. And again, you know, good to write all this down if you're doing it. So then the next thing is get some in your mouth. So you want to get it in your mouth. You want to let it warm up a little bit. You don't want to be too quick to swallow it. In wine, they do this thing called chewing their wine, which is they'll put it in, make a big face, do this. But the idea is to kind of get this stuff all over the inside of your mouth. And that's going to use your body heat to warm it up quickly, but it's also going to make a lot of surface area that these volatiles can come out. And then you can swallow it. And then after you swallow it, you do a retronasal. So let's do the first part of that. And then let it out. Because as the liquid is in your mouth, you're gonna get this sequence of events. The first things you're gonna taste, if there's any acidity, it's gonna be right there. Not gonna have a lot of salt in beer, so you probably wouldn't notice that. Sugar, the sweetness seems to kick in first because the bitterness takes so long to build. But about midpoint in there where I've got it all mixed up and I'm kind of starting to think about swallowing it, now the bitterness is starting to build. And I was once in a situation where we were asked to judge the difference between a 60 bitterness unit beer and a 100 BU beer. And the interesting thing about those two is that they were exactly the same for about the first 15 seconds. And then one of them leveled off and the other one kept going and just built up until that bitterness just was stronger and stronger and stronger. So with bitter beers, especially if you're judging IPAs or really evaluating an IPA, you really want to take your time and let that bitterness build up to its full strength. And then you're going to be left with this impression in your mouth. You can taste those I can taste these hop resins in here just clinging onto my tongue, making that bitterness, even though everything else is pretty much out. And then you also want to pay attention to the very end of the process. We've got the bitterness in there, but this is a place where if there's going to be any unpleasant tannic or astringent kind of flavors, this is where you're going to find them. So this is a real mark of quality in beer to not have that. It's generally not a huge issue, but there are certain types of beers made from barleys grown, in places like China or like hot weather or cold weather climate barleys that make beers that have a bit of an astringent kind of character to them. Even Budweiser, they make that from rice, which has a little bit of just a hint of a huskiness about it that they feel makes that beer a little crisper and more refreshing. It's that's the good side of a little bit astringent, right? Is that beer is a little sharp on the finish. And that's the way they have always liked to make it. But it's a really important characteristic that you might be easy to ignore. So now let's just talk about the retronasal. There's a lot of techniques for this. One is you can have that beer, you can swallow it and with your nose closed and then sort of sniff it out. I've never found that coffee guys use a process kind of doing a sort of a snort. I never got the hang of that, but they think it works. I find just best to just gently breathe out with your lips closed. And I find myself kind of pumping. I'll do a short breath in and then a long breath out and then a short breath in and a long breath out, and just like sort of on that kind of timing. And that sort of gives you multiple repeated hits of this retronasal flavor. And that seems to work for me. But again, it's your anatomy. You got to figure out what works best for you. So one of the things that you want to, when you're mid-taste or mid-smell, really all the smells, you want to pay attention to those olfactory memories. There's a chemical in beer that's another ester called isoamyl acetate. And it was the first artificial flavor to make banana candy back in the 1890s. Pretty widespread in beer and quite common in, say, Belgian beers often have it. Hefeweizen is famous for having a bit of a banana note. And usually when you give people this things with this banana ester, they don't come up with bananas right away. They go to banana candy, so it's like banana runts and things like that, because those are those childhood episodes, right? So people put themselves in the candy store, and then it's like, okay, what's in the candy store? So those little memories are really helpful to you because you can get in them and kind of explore them. And even though it might make no sense at all when you first come up with that, if you pay attention to it and kind of look around and figure out what might be there, then quite often you can come up with the reason why it smells like it smells. Yeah, I hope you found that useful. Just be aware that you can't read a book and become a good taster, that this is a physical, involving, psychological process that takes some time. There's a lot of aspects to it. It's really fascinating. It's really fun. If you're at all interested in learning to be a really good taster, I would highly recommend that you get out there and contact your local homebrew club, because they are always looking for people to judge homebrew, and they don't always require a lot of experience. So if you've done some reasonable tasting on your own and you feel confident to do that, I would highly recommend that, because that gets you in a structure that will allow you to do it. And really trust yourself. Know that you know more than you think you know, that your brain is taking care of you, your body is taking care of you. It's really trying to access that, use all that, trying to get yourself, train your conscious mind to employ the unconscious parts. Really realize that it's a journey you never quite finish, and that's okay, because who wouldn't mind another beer?